Okay, for the next example, this shaded region is what we're going to build our three-dimensional figure off of. It says this equation for this region is x equals y squared. We are stopping the region at x equals 9. Find the volume of the solid that has R as its base. So the shaded region is the base, and the cross sections are perpendicular to the x-axis. So you're going to want to draw a line that's perpendicular to the x-axis, and you can draw that anywhere that you'd like in this region. And the shape that you draw is going to be a semicircle. So a half circle, so this will be like the flat side, and then a semicircle. And that is supposed to be like coming out of the page. Obviously, if you draw a perpendicular line to the x-axis over here, the radius is larger, and therefore the semicircle will be larger. So the wider the shape goes, the larger the semicircles would be. Okay, so let's start with the fact that we have a semicircle. Now, what might help some of you is to maybe redraw the shape in a, normal looking two-dimensional surface. And then you could say, okay, this is a half of a circle. The area for a circle is pi r squared. Half of that would just be half times pi r squared. And then what's the radius? That's the next question, is what do I plug in? So the radius of the circle goes from the middle to one of the endpoints. And so if we look specifically right here, the radius would be the distance from the x-axis to the y value on the curve, okay? So this would be like the y coordinate of your function. And that means that this would be, we would have to go back and we would have to say, well, what is y equal to, okay? So if you were to solve this equation, y would be equal to the square root of x, correct? So the y value on the graph is equal to the square root of x. Okay, and then if we continue solving, this would make our equation the square root of x squared is x. So the area of each semicircle is a half times pi x units. And again, we want to find volume. That means that we are going to do the antiderivative, and this thing here basically will add up the area of all these semicircles in this 3D shape. The area sweeps from 0 to 9. And then you do your area of one semicircle goes in your integral. Okay, 1/2 and pi are both constants. So I think I'm going to kind of put them together and move that out of the antiderivative. That way I can just do the antiderivative of x. It's a little simpler that way. So antiderivative of x would be 1/2 x squared. And this is being evaluated from 0 to 9. I think I'm going to do 1/2 times pi by 2 and call it pi by 4. And now I'm going to plug in. So I have 9, and I'm plugging in 0, and solve. And let's see, this looks like it's going to be 81 pi over 4. All right, find the volume of the solid whose base is the region bounded by the lines x plus 2y equals 6, x equals 0, which is the y-axis, and y equals 0, which is the x-axis. Cross sections are being taken perpendicular, okay, to the y-axis. So this is a little different because we're going to go perpendicular to the y-axis, is like going side to side. And they are equilateral triangles. Okay, so equilateral triangles, let me get this out of the way. Perpendicular, so I'm going to draw a perpendicular line, and then I'm going to build an equilateral triangle on top of it. So equilateral means all the sides are the same, like that. In an equilateral triangle, the area formula for a triangle, let's start with that, is 1/2 base times height. In an equilateral triangle, the height is equal to radical 3/2 times the base measurement. Okay, so the base measurement in this problem goes from the y-axis over to the curve. Since we're moving from left to right, that would be the same as the x-coordinate of your function. And so if this distance is the x-coordinate, the height is equal to radical 3/2 times that value. So when we go to alter our area function for our triangle, the base is going to be represented by x, and the height is going to be represented by radical 3/2 times that amount. Okay, so then we could clean this up and we could call this radical 3/4 x squared. All right, now here's where everything changes a bit. I'm going to go ahead and I'm going to start my volume integral. And I'm going to write so far that my formula is radical 3/4 x squared. What changes is that the lines are being drawn perpendicular to the y-axis. So we're kind of doing the antiderivative with respect to y. The problem is that this variable is an x and this is being taken with respect to y. These variables don't agree. So a change has to be made. Okay? Now, it's not real hard to do, but you're going to go back and you're going to look at the equation of that line. The equation of the line is x plus 2y is equal to 6. I have an x here that I want to change to a y. So you will simply take that equation, solve it for x, and plug that in, that new equation in place of x into your integral. So that's going to look like this, radical 3/4, and then instead of x, you're going to have 6 minus 2y squared. Okay, what about your interval values? Your interval values, normally we go left to right, but the triangles are going to be drawn perpendicular to the y-axis. So the triangles are going to kind of go up instead of left to right. That means our interval values have to be y values. So we will have 0 to 3. That's clearly where the y values stop. They start at 0, they end at 3. So this is what your antiderivative setup would look like. Okay, before we can antiderive, we are going to need to simplify what 6 minus 2y quantity squared is equal to. And that's just using FOIL. So it'd be 36 minus 24y plus 4y squared. And now we can do our derivatives. So this is radical 3/4. I'm just kind of leaving that outside of everything. This would be 36y minus 24y squared divided by 2 plus 4y to the third divided by 3. And remember, we're evaluating this from 0 to 3. And then the rest of your work is just going to be a lot of arithmetic to simplify. Okay, so we end up with 36y minus 12y squared plus 4/3 y to the third. And then it's kind of up to you. If you want to, you can distribute the radical 3/4 now, or you could just keep it on the outside as you do your computation. I think I'm going to leave mine out and deal with it last. So I'm really just plugging in 3, because if I plug 0 in, every single term would be 0. So I just need to go through and plug in 3 everywhere that I see a y. And if you simplify everything inside the parentheses, you would end up with 108 minus 108 plus 36, add everything in the parentheses, you get 36, multiply by radical 3 over 4, and you get 9 radical 3. Okay, we have a region this time that it consists of a parabola and basically an upside down parabola. X squared is this purple line, 2 minus x squared is the red. We want to use the space between them as the base of our three-dimensional figure. To create our three-dimensional figure, it says to draw cross sections perpendicular to the x-axis, so that means vertical. We'll start maybe over here and draw a vertical line. That's the base of my shape, and we want it to be a rectangle with a height of 3. So I'm going to try, I'm going to try my best here, but I'm going to draw a rectangle, try to make it look like it's a little bit like oblong looking. Maybe I can do a better job over here. Rectangle with a height of 3. So maybe what I'll do is go ahead and label this as 3. All right. I like to go down here every time and start with what is the area formula for my shape. Rectangles are base times height. Let's modify and make it fit this particular question, okay? Well, we know the height is 3. The base of the rectangle is the distance from the top curve to the bottom curve, okay? So it's kind of like you're doing the area between curves situation. So what we would want to do is we would want to do the distance from the red curve down to the purple, which would be just subtracting the red function minus the purple function, okay? And simplify, this would look like 6 minus 6x squared. So that is the area equation for each rectangle. We want to add all those up. So we are doing an antiderivative to add all them up. The next thing we need is we need to know our interval values. Those are not given. The interval values, if they are not given to you, you will find them in this particular problem by computing where these two lines intersect. So we're looking for a point or points of intersection. Okay? To find points of intersection, it's real easy. You just take the two equations and you set them equal to each other. Solve for x. So this looks like it's going to be plus or minus 1. Therefore, the two graphs are intersecting at -1 and +1. Okay? Those will be the values that we use for our integral. -1 to +1. All right, now it's pretty routine from this point. So we're anti-deriving, we get 6x minus 6x to the third divided by 3. And we're going to plug in 1 first. Minus, plug in -1. Evaluate carefully. Obviously, you're dealing with a lot of arithmetic here, so you want to be real careful with your negatives and all that. So this would be 6 minus 2, which is 4. I'll come back to that. -6. This would be -1 times -2 is +2. So we have 4 plus 6 minus 2 if we run this negative through. And that looks like it's going to equal 8. Okay, and then let's look at one with semicircles. Another one, but this one's a little bit more involved. So we are doing volume of the solid whose base is bounded by the given function. So our function is a circle. And so all the space inside the circle is like this, the base of the 3D figure that we're about to create. Okay. We want to draw cross sections perpendicular to the x-axis. So that means cross section is going to go, supposed to be perpendicular, straight vertical line, and we're making semicircles out of them. So let's start with the area formula for a semicircle, which is 1/2 pi r squared. Okay. And then if you look at your semicircle, and sometimes it helps to draw the shape again, but the distance from the radius up is the y value, right? So this is the y value halfway. This is the y value, that's your radius. So we can modify our area equation and say that the radius is equal to the y value. And let's plug it into our volume integral. So I'm going to leave the interval out of it for a moment. I'm going to say 1/2 pi times y squared. Now we're taking we drew the cross sections perpendicular to the x-axis. Okay, so this means to be dx. These variables do not agree. Okay, we need to make them match, and that's where you go to your equation of your circle or equation of your shape, and you use it to help you. So how can I substitute something in for y squared? Well, if you just move some things around, y squared is the same as 4 minus x squared. So we're going to move some things around, and we're going to call this 4 minus x squared. And now all our variables are happy to say all agree. Okay. Also, in your circle, this number here is the radius value squared, which means that our circle has a radius of 2. Okay, that tells me that the circle or the space I'm creating for my 3D figure goes from -2 to +2 on the x-axis. So those will be your interval values. Okay, the last thing I'm going to do before I take my antiderivative is just move any constant values to the outside so they are out of my way. Now we can go ahead and integrate. So we have antiderivative of 4 is 4x, and then this would be 1/3 x to the third. Evaluate from -2 to 2. I'm going to leave pi by 2 out until the very end. And we would have, let's see, 4x squared, no, just plugging in the number, getting ahead of myself. Plug in your 2, so 4 times 2 minus, now I'm going to plug in -2. Okay, and then we can be very careful and simplify. So we would end up with, let's see, 8 minus 8/3, -8. This would be positive 8/3. I'm pretty sure -8 times, yeah, that's positive 8/3. And then simplify, looks like we would have pi by 2. 8 plus 8 would be 16. -8/3 minus 8/3 would be -16/3. I'll try to get a common denominator here. 16 times 3, that's 48. So we would have 48 minus 16, which is 32/3. And then we could just do top times top, bottom times bottom. Both of these can be divided by 2. So we get 16 pi divided by 3. Okay, there are a few more examples left in your notes that I did not get to. What I'm going to do is post a PDF with all of the work shown for these examples. So maybe take a look at those, and then that should hopefully help you get started with your Delta Math homework.